Hello and welcome back to Calculus 2, section 11.4 on calculus with power series and Taylor series primarily. So today we are going to take a look at some details. Very simple idea here. You take the Taylor series of the function, which gives you the polynomial, and then you just integrate or differentiate that polynomial. It's a very simple idea. But then we can also do some more details and so on. The first thing that I'm going to do here is to do the proof for the derivative of sine x, right? So if you have your derivative of sine x, instead of doing the x plus h and blah blah blah, right, we can just write the sine. Let's say we write out four terms: x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus dot dot dot, going forever. And now you just take the derivative of each one of these polynomial terms independently, right? So derivative of x is 1, and then you have minus derivative of x cubed is 3x squared over, and 3 factorial you can write as 3 times 2 factorial, plus 5x to the 4th, and then you have 5 times 4 factorial, minus 7x to the 6 over 7 times 6 factorial, plus and I hope you see why I decided to peel off one of the factorials, because they will all cancel. So 3 cancels 3, 5 cancels 5, 7 cancels 7, and what you get is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus dot dot dot, going on forever. And when you take a look at that, that's the power series for cosine x, which is awesome. And let's say that you want to find now another derivative, the derivative of cosine. You would see the derivative of 1 is 0, and derivative of x squared is 2x and cancels the 2, so it becomes negative x. And you get a series for the sine, but the signs are backwards, but we know the derivative of cosine is negative sine, so click, right? So it's really awesome. What is the derivative of e to the x?
E to the x.
Can you please prove that to me by writing out 4 terms, differentiating 4 terms?
Oh, yeah.
Right? So I did suggest you memorize sine, cosine, and e to the x, those 3 as power series, to memorize at least those 3. If you're going to differential equations, then just expand your brain into sine and cosine hyperbolic, because they will be very beneficial in DFQ. So if you are going to differential equations, then definitely remember those 5. And then after that, there are like 3 more that you can do if your brain is big enough for these things. So power series of e to the x, right? We'll just write 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot. And when I apply derivative, I get 0 plus 1 plus 2x over 2 plus 3x squared over 3 times 2 factorial plus dot dot dot. And when I cancel a 2 and 2 and 3 and 3, you see that you got back 1 plus x squared over 2 factorial plus dot dot dot. So you got back your e to the x. Now I would like you to stop for a second and just realize that someone figured this out.
You did?
No, someone. This is welcome to being 200 years behind current mathematics. But, but you know, there was a person at some point who said, "Oh, yeah, this is obvious."
That's what happens when you don't have cell phones or anything.
Oh, no distraction,
No
exactly.
distractions. You just sit there and read.
They didn't even have the toothpaste and toothbrushes at that time, man. Like, they had nothing. 1800s? Come on. Right? So this should be before 1850, these results. All of the sequences series, power series, all of that stuff, including Calculus 3 and most of differential equations. Everything hovering 1800s, early 1800s, before 1850 and so. Development of linear algebra starts in late 1800s and early 1900s. So, you know, before the First World War and so on, it's linear algebra development. So once you hit linear algebra course, you will be about 100 to 150 years behind and so on. Cool. So now we understand this. Now, how do we integrate? Well, we integrate the same way. So if we want to integrate something that cannot be integrated easily by hand, we discussed already this problem, e to the x squared, because you need an x in front to run u sub, right? And nothing else would work. Obviously, trig sub and partial fractions are out because this is not one of those type of problems. So technically, you know, you can try and waste some time trying to figure out this using the integration by parts, and then when you fail there, then it's just, okay, what, right? Well, there is something you can do in Calc 3, but that's Calc 3 when you have multivariable calculus. So we're not going to worry about that stuff. What we are going to worry about here is obviously the series. Now, we don't have a series for e to the x squared, but we last time had that theorem which said that you can do function composition, right? So you do have series for e to the x, and then every x of the series will be replaced by x squared. So we do have e to the x as 1 plus x squared over 2 plus x cubed over 3 factorial, which is 6, plus dot, dot, dot. And I did tell you, just keep the 4 terms and, you know, leave it right there. So now that we have this, we are going to, instead of x, put x squared, which will replace x squared everywhere in the thing over here. So we'll have x squared over 2 plus x squared cubed over 6 plus dot, dot, dot. And now e to the x squared is just 1 plus x squared plus x to the 4 over 2 plus x to the 6 over 6 plus dot, dot, dot. And we integrate that one instead. So we are integrating in parentheses 1 plus x squared plus x to the 4 over 2 plus x to the 6 over 6 dx. And as you can see, I cut off the plus dot, dot, dot. And, well, actually, you can add plus dot, 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 whatever. And what we have now is integral of 1 is x plus x cubed over 3 plus x to the 5 over 10 plus x to the 7 over 42 plus dot, dot, dot. So that's, and then you have your plus c. Now, generally, we would put plus c in the front, so this dot, dot, dot doesn't bother it. But you can put it there, so it's fine. And this integration comes in with a very big red warning sign, and that warning sign is if you have definite integral, be very, very careful, right? So if I have to calculate e to the x squared dx from, let's say, 3 to 3.1, how's this different than the previous problem? Okay, so we're not going to use dot, dot, dot. We are going to actually just do the 4 terms, let's say, so we can actually compute the value and have the, that's perfect. And what else?
We don't use a constant at the end.
There will be no constant at the end because we'll compute definite integral, sure. There is something major before both of those that you guys suggested. So both that you gave me is
It has to
correct.
be centered between 3 and 3.1.
Yes, it has to be. You can center it at 3. If the range is wider, then you can maybe center it in the middle, right? So if you go 3 to 4, then maybe centering 3.5 makes sense. But 3 to 3.1, you can center it at 3. That is crucial. You cannot cut and paste the polynomial from up there and solve this. You're going to get disgustingly wrong answer. All right? So in blood, power series must be centered at 3. So you'll have your x minus 3 in parentheses. If you don't do that, all hell breaks loose. These numbers will be off. Remember those graphs that we had, right, for sine and cosine, and how the polynomial used to snake around it, but then when it kind of runs out of luck, they just go far apart. It happens for every single one. As soon as you cut it off sufficiently far down the x-axis, they're just going to go and diverge. And that can happen for this, right? So you must, for definite integrals, you must center at 3. So you are using the same polynomial, you're just writing x minus 3. So, cut and paste. Control C, Control V, and then just edit minus 3 for each one.
That's the only thing that you would change.
That's it?
X minus 3.
Yes, because, you have to be careful where to center it, right? The limits will tell you.
Oh, okay.
We are centering at 3 because limits are 3 to 3.1. If the limits are 7 to, let's say, 7.5, you can center it at 7.
Okay.
Or you can center it at 7.3, whatever. You have to center it. For small intervals, center it on the lower limit. For larger intervals, maybe center it in the middle.
So it'll kind of be smarter to center it at the lower bound so that it...
If the interval is low, because this is 3.1. But if it's 3 to 4, then 3.5, right?
Wouldn't you rather just add another term then? Because if you use 3, then whatever you're going to subtract is going to be 0.
You can, but again, you have to understand why we do this, right? We are doing this because A, we can integrate, and B, we really don't want to sit and integrate forever. Adding extra term are high-end calculations rather than, right? So you always, anytime you do any of this stuff, you always have to think computer science, always, right? And the least amount of operations you get to do is the most efficiency in your software, right? So adding an extra term, yeah, it's not going to be an issue for one calculation for you on a test, but remember that a computer is going to perform 100,000 calculations, right? So to integrate the term and plug in on the 2 points, right, and how many operations, you might be introducing maybe 10 operations per cycle times 100,000, right? So you get 1 million, right? Calculations added to your calculating cycle just by adding an extra term. And that makes your software slower, right? So your competitor beats you in that. So you have to be very careful with these kind of decisions. You do not want extra terms unless you absolutely must have extra terms, right?
That's 4 kind of like the standard.
3 to 4 is standard for engineering applications. Because the precision is already good enough, right? And it's better to play with the interval because interval is something that you have to use anyway, adding an extra term adds extra calculations always, and adds a lot. That's why we generally, right, because look at a term. There's one calculation to square this, there is another calculation for the factorial, there's another calculation for division. So you have 3 calculations just there, plus the term is added, that's the 4th one. You had to integrate it, which is an algorithm, right? And then times the amount of times you have to do it. So it really kills the productivity, right? We do not add extra terms unless we absolutely must. But to give you full credit, you are completely right that adding extra term would fix a lot of, and when you have to do it, you have to do it. I mean, that's, especially for large intervals, like if the interval is 3 to 4, 3 to 7, holy nightmare, 3 to 7, you have to include a lot of terms there. But in calculus and calculus, in chemistry, in physics, in all of these, right, the changes are always small and subtle, and right, so we don't, right, we use these usually to observe the change and growth that we sometimes can't even spot by eye, right, or change over time. Yes?
So as with everything else, if it drops below like the x-axis, then we would break up the function.
That stands for area under the curve. So all of the applications from Calc 1, everything stays the same, yes. If it dips below, now we know that e to the x is always above, so we don't have to worry about it at all, but,
Like sine or cosine.
Yeah.
A definite equal on that.
Mm-hmm. But that's, again, different applications have different requirements, right? Some of the applications actually don't care about it. So, yeah. Maybe you do need net energy. In that case, you don't have to worry about the, right? That chapter, yes?
So, like, what if I wanted to center it at like 3.05?
You can, it's just, you can, you can, right? But again, it's just gonna be extra annoying calculation because this was a small interval, you could have just used 3.
Okay.
If you wanna do it as a rule of thumb, you can.
Okay.
But in some cases, it's not necessary, so using 3 is much easier than using 3.05.
Right.
But you definitely don't want your problem 4 to 7 to be centered at 4.
So if it's like less than 1, or like...
Not even less than 1, like, I don't know, 0.5, 0.4, something small.
Okay.
Again, relatively small, that's also relative term. Remember we said everything is relative?
Yeah.
Because, how small is small? That's the thing. I mean, the size of an atom is 10 to negative 15. And my size, right, is 1 because measured in meters, right? I'm a unit. In our units of measurement, I'm a unit, and the atom is 10 to negative 15.
Negative 23.
No, 10 to negative 15 for size. I'm talking for the size, not.
Moles is the 20.
Yeah, that's moles. You're talking about Avogadro's number. I'm talking about the size of the radius of the atom. So we are talking order of magnitude of 15, right? 10 to the 15. That's not 15 times. 15 times is, right? You divide my height in 15, and you're still gonna see, right, the 15th part of me. So that's not a big, right? It's not a big deal. But it's 10 to 15. That is a huge order of billions. Yeah. All right, good. Let's hit the break. After that, one section of chapter 12 and